So, as we have mentioned that coke is made in the coke ovens. So, usually there are two types of coke ovens used in coke making. One is slot type and another is beehive type. Slot type coke oven, where you put the coal in a chamber and indirectly, because cooking has to be done in absence of air. So, indirectly you provide the heat from the side. So, these are the side chambers. So, clean coke oven gas or pre-warmed combustion air, it comes heated up. So, from the side you are providing the heat to this coal. So, cooking occurs from wall to the center in this one. And once the cooking is over, this is pushed away and taken it out. So, you have different type of ovens, you have not different type, many ovens like this. So, the whole sort of ovens in a row, it known as the coke oven battery. So, whatever gases and other things which is evolving during the coke making, these are taken away from the top in the slot type oven. Beehive oven, these are known as some non-recovery oven also. The reason in this one, when you say non-recovery, essentially it is not a very non-recovery, but in terms of pollution, just it reduces the pollution. So, what is happening in this, you provide the heat from the bottom and from the top and with less air. So, whatever gases which are tar or aromatic compound which are evolving during the cooking process, they are burnt at the top, and that heat is being utilized to supply to make the cooking process. So, in this one it is just going out and then you have to process them. Here most of them you are burning over there and utilizing it. So, that is how these are called non-recovery coke oven. And then the whatever hot gases are there, they are used for electric generation and other things. So, still you use those gases and you have to treat them, but essentially you are using quite a lot what is coming out from the cooking process in heating up the coal. So, nowadays many modern plants are trying to use the non-recovery coke oven or beehive coke oven. This is a typical figure of one of the coke oven battery. As I said, when you put a series of these coke ovens, you usually call them as a coke oven battery. So, this is one of the oven where cooking process is occurring and cooking is almost over. So, from the side these are you supply the heating, and once the cooking is over, so from the other side you push the coke, the hot one, and collect it in a container. So, that is after the cooking process is over, you collect it here, and after that you do the quenching, because you can't leave it that, it will oxidize, it will react with the atmosphere. So, then you do the quenching, and quenching it said it could be wet or dry. So, either water spray or coke dry quenching. Water spray again it is not environmental friendly, it used to be done like this because it generates lots of dust and other thing. A new quenching technology has come, which is called the coke dry quenching CDQ technology. So, in which the hot coke comes in that container and you blow the inert gas through that cold one, and which cool it down to an acceptable temperature about 200 degrees Celsius, and that can be then sent to the blast furnace without further oxidizing in the atmosphere. And that's hot gases are used generate electricity or any other thing, steam and thing you can use it. So, in this way this does not generate that much dust and pollution, and nowadays people are using mostly this technology coke dry quenching in the modern steel plant, but old plant are still going with that one. So, pre-carbonization technique. So, preheating. So, now before we do the coking, there are some other thing which one has to do depending if you do not have a very good quality coal, or you can increase the efficiency of the coking or make a good quality coal using these techniques. So, one is preheating of coal between 180 to 250 degrees Celsius to improve the strength and bulk density of the resulting coke. So, when you do the preheating, moisture and other thing goes away. So, in that way the bulk density, so it becomes more compact when you put it, strength increases. So, naturally you get a little higher bulk density of the resulting coke. Briquette blending of coke. So, when you do not have a very good quality coal, then you use this briquette blending of the cokes with the poor coking constituent are briquetted and blended with the rest of the coal. So, improving the bulk density and strength of the resulting coke after carbonization. So, this again increases the bulk density. Briquetting is like making a sort of a cylinder by applying the pressure into that. So, you increase the density of the material, and that is the one when then you charge it. Stamp charging, again the bulk again to increase the density of the coke, final you apply these other techniques, because the bulk density is also quite important. This gives the strength to the coke. So, stamp charging, bulk density of the coal charge into the oven is increased by stamping the charge into the coke outside the oven. So, what you do, you take a coal, you stamp it and outside the oven actually, and once this is ready, then you dump it in the oven. So, these all are done outside the oven. So, low rank, weakly coking and high volatile matter coal can be used to make the coke for that purpose. So, especially when coal is not very suitable, then one of these techniques or all of them can be used to make them suitable for the blast furnace. Coke quality assessment. So, that depends on many parameters, as we discussed many tests for the iron ore, sinters, pellets. Similarly, for coke, some of them are the same which we discussed before, but some of them are different. Chemical composition. So, as I said, these are done with the proximate and ultimate analysis, which is important to determine the ash content and other elemental content. If it has a higher sulfur content and like that, one cannot use, because that will create the problem later on. Reactivity of the coke, the rate at which coke carbon reacts with oxidizing gases like oxygen, CO2, air or steam. So, really we do not need a very high reactive coke. If highly reactive coke is there, then it has to travel from the top, from the throat to your level, and if it is highly reactive, by the time it will reach to the tier level, it may not have sufficient strength and the permeability or porosity to withstand that one and give a proper passage for the gases to escape. So, what we need not a very high reactive coke, because this is in terms of design for hot strength, increased degradation, decreased coke size in the lower part of blast furnace, and that will also increase the coke rate. So, tests are Nippon Steel Corporation test, NSC, coke strength after reaction, CSR or coke reactivity index. These are the few important tests which are required to see the coke has the desired reactivity. Thermal stability at high temperature. Thermal stresses are developed at high temperature, and that can actually decrepitation can happen. So, for better thermal stability, not a very large size uniform, so you do not need a very large size coke, uniform texture, high carbonization temperature and low chemical reactivity. These are the important thing for the coke to become a feed material for the blast furnace. So, like in the charging zone, coke goes into this impact stress abrasion. So, what you need is size distribution, resistance to breakage, abrasion resistance. Granular, that is a stake region. Again the gas permeability is very important, reaction and preheating, all those things are occurring. So, alkali deposition, mechanical stress, abrasion, through these it goes through. So, what you need? Size and stability, it should maintain the size and stability, mechanical strength, abrasion resistance. Cohesive zone, very important. Here is the gas permeability it gives, Verdun support it gives, and in slag drainage. So, gasification by CO2 and abrasion, this resistant to this, it is very important. If it does not have, you know what will happen, no gas will pass through the furnace and very high pressure drop it would be, and then you have to stop the furnace in some cases. So, proper size distribution, low reactivity to carbon dioxide, high strength after abrasion. Active zone, again these are the function of the coke. So, degradation in this one, CO2, abrasion, alkali attack and S reaction. So, size distribution, low reactivity, abrasion. Railway zone, combustion occur here, thermal shock, graphitation, impact stress and abrasion. So, strength against thermal shock, because thermal shock is due to the thermal stresses which comes, and due to that it may disintegrate, you do not want that. When we were looking at the picture of dissected blast furnace, you have seen after the raceway region you see quite a big deposit of a small particle coke, that is mostly by abrasion and disintegration that occurs. So, mechanical stress, abrasion resistance. So, these are the requirement of the coke. In Hertz zone, of course, it gives a Verdun support, iron slag drainage, carburization of iron, graphitization, dissolution into hot metal, mechanical stress, the requirement, size distribution, mechanical strength, abrasion resistance, carbon solution. So, mostly you can see the size distribution, abrasion resistance, mechanical strength, low reactivity, these are very important for proper blast furnace coke to become a feed material. Now, strength and abrasion resistance has to undergo a rigorous handling and charging from the coke oven to in front of the tuer. Therefore, strength and abrasion resistance is measured using the SETA index or abrasion indices. So, this of course, we have discussed a bit in iron ore sinter pellets. Here especially for the coke, the test is Micom drum test, IRSI test or ASTM 1, and these are the typical the size distribution, you get it, accepted range, harmonic mean size, arithmetic mean size, and the cold strength, these are sort of a test you do it, and the best value is indicated over here. Similarly, stability in the stockyard and other places, strength after the reaction, so cold strength reactivity, this NSC test, reactivity NSC test, and the best value of those. So these summarizes what the good coke to become a feed material for the blast furnace should have the values. So this is very important. We'll give you a one practice numerical on mass balance in modern iron blast furnace or iron making. We will take now few numerical examples. The first one is an iron ore processing plant related. As you know, all theory are useful if they can be put into practice, and that is why these numerical examples have been taken from the real practice, from the real plants. So the first one tells about an iron ore processing plant lists its output in terms of content iron. If it is shipping 1350 metric tons of iron per day, how many metric tons of magnetite is that equal to? So many times this sort of problem comes in the plant that they talk in some other unit and which probably you do not know in a proper way. So how do you convert in terms of the right unit? So 1350 metric tons of iron in terms of magnetite. So what essentially you do, you know the formula of the magnetite considering this Fe3O4 as a pure compound. So stoichiometric ratio, as you can see, 1 mole of magnetite is having a 3 mole of iron. So molecular masses of these one would be, for magnetite it would be 231.54 tons per ton mole. You can put it like kg per kilomole, grams per gram mole. These are the normal unit which you put the molecular masses, and for iron it is 55.85 tons per ton of mole. So gravimetric factor, what it gives, because we have a 3 moles of iron. So molecular weight of or molecular mass of the magnetite divided by molecular mass of iron by 1/3. So we have a 13 in the example 1350 metric ton of iron per day. So 1350 metric tons iron per day, and you multiply with this gravimetric factor. So essentially what you will get 1865.7 tons magnetite per day. So the question is, how many metric tons of magnetite is that equal to? So that will give you the so many tons of magnetite per day which is shipping. It just a one very simple example, but very useful in the industry and converting into the proper unit. So one can understand. Is another example which is more related to beneficiation, and this is the iron ore is beneficiated using magnetic separator to increase the overall iron content in the ore. We have already discussed about magnetic separator during beneficiation when ore is lean and we want to increase the concentration of the iron content in the ore. So, usually we take various type of beneficiation processes. So, one is magnetic separator. So, this is related to that the problem. So, an ore containing 40% hematite and 60% silica is subjected to magnetic separation, because already the so already you will see the percentage of hematite is quite low. So, we have to increase that. So, after separation, tailing consists of 85% silica and concentrate consists of pure magnetite. If the mass flow rate of the ore is 1 ton per hour, find the mass flow rate of magnetite in the tailing. I am sorry, actually this is a magnetite. So, we have this magnetic separator. So, 40% magnetite, 60% silica, that is input. So, always when you do any sort of a material, so mass balance or heat balance, it is good to have a sort of a box and indicate what is in and what is out. That gives a very good idea what is going on into the reactor and what is coming out. So, you can do a proper either a material balance or heat balance. So, in this case 40-60% is going in at per ton in 1 ton per hour, and the concentrate which is coming out is magnetite, which is 100% as it is given in the problem, and tailing is having 85% SiO2 and 15% magnetite. So, now because we have a 1 ton per hour, which is 100 kg per hour and 40% magnetite. So, we can know how much magnetite per hour. So, 0.4 and 0 kg magnetite per kg of ore. So, that is going to give you about 400 kg magnetite per hour, which is going through the magnetic separator. Similarly, we can get the silica in terms of kg per hour. So, 1000 kg per hour with 0.6 or 60%. So, 0.6 kg silica per kg ore, that is going to give you 600 kg silica per hour. So, this is sort of a mass flow rate of both the species. So, all silica is given, it goes to the tailing, because the concentrate is the pure one. So, which means the all silica is going to the tailing, and which is forming the 85% of it. So, rate of tailing, so 600 kg silica per hour we have already find it out. So, 85% actually is going in the tailing. Tailing is containing 85%. So, which means the flow rate of this tailing would be 7. So, you divide this 600 kg silica per hour with 85% silica, because this constitute 85% of the tailing, will give you the tailing flow rate. And once you know the tailing flow rate, then you can calculate the magnetite which is leaving with the tailing. So, this is the flow rate of the tailing, 705.9 kg tailing per hour, and you multiply with the 15% remaining magnetite which is with the tailing, 0.15, will give you the magnetite which is going into the tailing per hour. So, 105.9 kg magnetite in tailings per hour it would be going. So, rest of the magnetite naturally is going as a concentrate. So, concentrate would be having then 400 kg minus 105.9. So, about 294.1 kg magnetite in concentrate per hour. So, that is a very simple mass balance by which you can calculate how much magnetite is going to the concentrate and how much it is going into the tailing, and you can easily calculate that one. So, these are few simple example I gave. Now, another example which is coming in more realistic example, it is related to iron making blast furnace, which we have talked till now, and the question is in this one, an iron blast furnace in steady state produce 8,000 ton of pig iron per day. The analysis of the pig iron was 93.1% iron, 4% carbon, 1.18% silicon, 0.9% phosphorus, 0.8% manganese and 0.02% silica sulfur. So, iron ore charged into the furnace contained 72.2% hematite, 9.6% silica, 7.8% Al2O3, 6.2% water, 3.1% manganese oxide and 1.1% phosphorus pentoxide. So, the coke used contain 88% carbon, 9% silica and 2% alumina and 1% iron sulfide. We also put the flux. So, the limestone flux having composition 96.5% calcium carbonate and 3.5% silica. The input rate of coke and limestone was 6,000 and 5,000 tons or 4,000 tons per day respectively. And furthermore, 98.3% of all the iron entering the furnace was accounted for pig iron. So, you have to find out the input rate of iron ore and the output rate and composition of the slag. So, in this one again you can make a box diagram of materials balance where you can show input and output, but it would be good if you work out this thing in the form of table and use some Excel sheet or something, and that will facilitate the calculation. The way probably which we can do it, we represent all these value in terms of weight percentage of all the element. For example, hematite, in this one we can represent iron in terms of weight percentage. So, iron in Fe2O3, so it is 72.2% Fe2O3 is there in raw material, and we know the molecular weight of iron is about 56 and molecular weight of hematite is 160 that we are considering as pure. So, iron in hematite or Fe2O3 would be 72.2 into 2 because there are 2 moles of iron. This of course, we did in the previous example also we showed this one. So, 2 into molecular weight of iron divided by the molecular weight of hematite 160. So, that gives you the iron in hematite 50.54 weight percentage. So, similarly, you can do the calculation for other elements silica, aluminum, hydrogen, phosphorus, manganese, calcium, sulfur. So, whatever other element which are present in this example, one can make similar calculation for weight percentage and which can be put in tabulated form like this. So, the data from this data construct a following table in terms of weight percentage. So, here you put the material input. So, input is going iron ore, coke, limestone, and output is pig iron, slag and the gases. So, amount tons per day which we are putting, we do not know iron ore, that we have to find it out, that is given in the question, but coke rate is given 6000 tons per day, limestone 4000, pig iron production 8000 ton per day, slag we do not know, and gas also we do not know, but that is anyway not required, it is not the question, but we need about the slag output, we have to know amount. And then if you write it in terms of weight percentage, as we have shown in the previous slide, these elements you can put it. So, in iron ore you have iron, silica, alumina, manganese, phosphorus, oxygen and hydrogen, but like in coke you or in the coke you are having some sulfur, so where sulfur is also coming, and limestone you have calcium, calcium is also coming over here. Similarly, in pig iron composition is given, you have iron, silica, manganese, carbon, phosphorus and sulfur. Slag we do not know the composition of any of these elements, so we have to find out. So, small letter in the table denote the unknown composition in weight percent, and capital letter denote unknown amount of respective materials in tons per day. So, once we construct this table in terms of weight percentage, I think it is easy to do the mass balance now. So, what is, let us say for iron. So, mass balance for iron would be iron is coming. So, input is from iron ore, the iron is coming. So, this into this, from coke iron is coming. So, this into this, and there is from nowhere else the iron is coming, but iron is going out in terms of pig iron. So, this into this. So, this should be equal to this into this plus this into this. Also iron we are getting lot in slag. So, that is a calculation. So, input equal to output, conservation of mass. So, materials balance which you do it. So, consider the mass balance for iron. So, iron in iron ore and coke. Similarly, output iron in pig iron and slag. So, as I have shown you in the previous table. So, this would be the valence for the iron. Now, 98.3% of all the iron entering this furnace was accounted for pig iron as given in the problem. So, this is already given to us. So, hence iron in pig iron divided by iron in slag should be in this ratio. So, remaining 1.7% goes into the slag, when 98.3 is going into that. So, this gives you, when you do the calculation, the iron in slag is and by solving these two equations, you can get the amount of iron ore input. So, you get the input rate of iron ore in that way, 14,915.7 tons per day. Once we know that, then we can calculate the iron in the slag by finding that. So, you get it 149 tons per day. Similarly, you can calculate other elements present in the blast furnace. For silicon, you can do the mass balance, and then silicon input in the slag, manganese input in the slag, aluminum, phosphorus, and phosphorus, all the phosphorus goes, as you will see in this one, all the phosphorus is going to the pig iron. So, really you do not get phosphorus in slag. Calcium you can get that, and sulfur also you can get in a similar way. So once you get this, you can calculate even the percentage form. So now in terms of composition, what we need a sort of a conversion factor. So molecular weight of metal oxide and molecular weight of the metal. So in terms of hematite in slag, so iron in slag, conversion factor. So iron in slag from mass balance we know 149.15 tons per day. So conversion factor, because this is coming from Fe2O3, so 160 divided by 56, it's going to give you, so no actually though this is this one, but actually iron in the slag in the form of FeO. So you have to consider about the FeO. So molecular weight of metal oxide, FeO is 72 divided by molecular weight of metal 56 multiplied with this iron in slag. So it is going to give you FeO in slag 191.76 tons per day. So total slag that when you convert in terms of percentage, these things you will find from the table in the next slide, is about this amount. So when we know the total slag, we can convert the percentage. So FeO in slag is this and total amount of slag is this, that is going to give you 3.25% FeO in the slag. Similar calculation we can do for SiO2, for CaO and other oxide which are present in the slag. So mostly FeO, so we got 3.25%, then you have SiO2, you have Al2O3, manganese oxide, calcium sulphide and calcium oxide. These are the oxide which are present in the slag. So in a similar way we do the calculation for these other oxide, you can then calculate the percentage of these oxide into the slag. So as we said, once we know tons per day, so we can calculate tons per day for all of these oxide and we can add them up, so we can get the total slag. So total slag actually is made of this, and that is how then this divided by this we get the percentage. This divided by total amount of slag, you get this percentage. So like this you can get the percentage for each of the oxide, which comes around 100%. So you can see the silica and lime is the major, silica, lime and alumina is the major constituent of the slag in this example. And this actually can be done more easily if you use the Microsoft Excel program. So on Excel sheet you can easily do these things, you put the values and conversion factor and other thing, and you put the formulas and you can immediately get the results of that. So it would be good for a complex problem like this, one should use the Microsoft Excel program, and that would be much easier to solve the problem after putting the things, and even the composition changes, you can see the effect of various element also. If you change it, what would be the composition of the slag and like that. So now we will come to the next topic, which is about the auxiliary fuel. And as you know, we talked about coke as a, it acts as a fuel, but as we mentioned, coke is very expensive and environmentally not friendly to make the coke. That is that's why there are worldwide effort to substitute coke with other fuels, and that is why this topic is auxiliary fuel. So, there are many attempts going on worldwide to substitute coke with other fuel like oil, coal, plastic, biomass, natural gases. So, we would be talking some of these thing over under this topic, because the coke making is a very nasty process, and environmentalists are against it, and it is not only that, we know it is quite a pollutant, and we have to find out some sort of alternative to the coke, and one of these to use the auxiliary fuel through the TUA, because coke cannot be currently replaced 100%, because it provides the mechanical support to the burden. When our blast furnace is so high, there is no other material which can give that sort of support and which can withstand also that high temperature. But certainly we can reduce the amount of coke, and that is the effort which is being made, and we will be discussing in this. So, auxiliary fuel, when we say, the name suggests, it supplement the main fuel supply, that is coke of the fuel, coke of the blast furnace. So, main purpose is to reduce the coke consumption rate in the blast furnace, and you can reduce only up to some extent. So, that is the effort, that how much we can reduce. We will actually do some more calculation on that how much coke really we can substitute by other supplement fuel, because not 100% coke can be substituted by this. Oil, gas and pulverized coal are used as auxiliary fuel in the blast furnace. Nowadays, even this natural gas or biomass, municipality waste, treating them and using it is going on at few places. So, as these fuels are economically viable in production of hot metals and reduce the environmental impact in comparison to coke oven, they are being used increasingly. So, pulverized coal injection is becoming the integral part of the modern blast furnace. Therefore, coal for pulverization and injection should have the following properties. So, PCI injection, in fact, most of the modern blast furnace, it is an integral part now, like a coke oven or cleaning of the gas and like this. Similarly, this is also now becoming a part of the blast furnace. But to inject the pulverized coal, it should also have some qualities. First one is the low sulfur and phosphorus content, that is very important to control the chemistry of the slag and the chemistry of the iron, pig iron, and subsequent operation of steel making, and that we had discussed before during the iron ore and coke preparation. Low volatile matter it should have, then it should also have the low moisture and ash content, and it should have a smaller size. So, ash content certainly is always a problem, as we discussed in coke also. So, ash because it will increase the volume of slag and create some other problem. So, ash should be low and moisture should be low. We do not want to use the fuel just to heat it up and go best in this, and size has to be very small. So, this is a very critical parameter in PCI, because the injection of that PCI when we do it in the blast furnace through 2 years, it has to burn within millisecond, because the velocity is very high, and due to that within 4 or 5 millisecond it has to burn. So, size is a very critical requirement for pulverized coal injection. If size is higher, then it will deposit in the upper part of the blast furnace, and we reduce the permeability and the operation problem will come. So, usually size is about between 75 to 100 micron. So, this is a schematic of pulverized coal injection unit. So, as you can see, the waste gases and other thing comes over here, coal field. I am not going to talk much into that, but main thing after this fine coal silo pulverized coal comes, it goes through the transport air to the distributor, and this is also a very critical part, because this distributor has to make sure the coal which is being delivered to all the tiers should be consistent. So, the amount which is being delivered to all of them should be consistent and proper, as you might have in fact this thing we discussed during the dissection of the blast furnace, and we saw even a one coke one tier is off, there is a big difference in the internal structure of the or internal aerodynamics of the blast furnace. In a similar way, if the right amount is not being fed from each tier, then the chemistry and aerodynamics will change of the blast furnace. So, this is a very critical part of the pulverized coal injection system, that it must deliver to all the tier in a right amount. As you will see in this slide, the coke it takes about less than 5 millisecond to burn. So, and during that 5 millisecond you can see what happens: evaporation of moisture takes place, heating of coal, gasification of volatiles, ignition oxidation of volatiles, ignition and oxidation of char. All these things have to happen or finish within 5 milliseconds. So, it is very critical it should have a proper size, proper hardness and other property. We have discussed few of the properties during the coal selection and other same sort of properties it goes here.